All right, in section 3.2, we're going to continue to explore the normal curve. And on 3.1, we learned about how to find the center of the normal curve. The center, which is basically where the hump is located. And in section 3.2, we're going to learn about its width. So we're going to start with a picture. Actually, I want to start with a picture up here. In this course, the whole point of this course is to take a population, which could include many, many, many people, and break it into what we call samples of smaller amounts of people. And then we use these samples to predict what the overall population looks like, since we can't talk to everybody. And in this section, we're going to look at things like mean. Let me get a list going here. So we have mean, we have variance, and we have standard deviation. And then we have for the population, and we have for sample. And there's just some symbols we have to learn. So for the mean, you might think of it as the average. So what's the average value of all the people in the population? The mean value. We use the symbol mu. It's a Greek letter. It looks like a U with a tail in front, and it's pronounced mu, M-U. So that's the symbol we're going to use for that. So that lives over here in the population bubble. But for the sample, and we saw this yesterday, we use X bar. So we use an X with a bar above it. And that would be the sample mean. And those live inside these sample bubbles. And I can have different ones. This would be 1, this would be 2 for sample 1 and sample 2. Variance, and we're going to learn what this is today. Variance, we use the Greek letter sigma, and that looks like a circle with a tail on top, and it's squared. So this is sigma squared. So this is the Greek letter sigma. In a sample, we just use the letter S for variance, well, S squared. Why do we use the letter S to represent variance? Because we use the letter S to represent standard deviation. So the S stands for standard deviation, and then variance is just this value squared. And so these values would also live inside these sample bubbles. Okay. And then sigma squared would live in the population bubble. And then finally, standard deviation for the population is just sigma. So notice, we're going to be mostly interested in these two, because I can get to variance just by taking the number, whatever number this is, and squaring it. But what does standard deviation and variance really mean? That's what we're trying to figure out today. So hopefully this idea is clear. We have a population, bunch of people, we break it into samples, we take measurements on these samples, we get these statistics, these numbers, and we can use those to then predict what these numbers would be. Okay, so let's take a look. Question?
What is that by the mean underneath population?
Right here. This is the Greek letter mu, M-U, and it looks like a U with a tail in front. Yeah, it's kind of a, so this is now where we get into math where we start to use Greek letters to represent things. Okay, so when I was a young engineering student, my teachers just assumed I knew what these Greek letters were and they started using them and I had no clue. So when I teach this stuff, I try to explain to you, this is called mu and it looks like a U and it has a tail, right? Because they can be a little foreign to us, right? We probably haven't seen many Greek letters before. Okay, so let's use a picture though. That's going to help us understand this even better. What we're trying to do is this. When you have a normal curve, it spreads out. So it has a certain spread, which is the width. And the way it works is like this. So the very center, and I'm going to do this twice. So this one's going to be for a population normal curve. For the population normal curve, we're going to use these Greek letters over here, mu and sigma, etc. So the very center of this is the mean. So the very center would be the Greek letter mu. Then it increments equally by 1 sigma. So this tick mark here would be mu plus 1 sigma. And again, these are just numbers. So if I'm dealing with height or something, I can say average height is 70 inches with a standard deviation of 2 inches. So this would represent 72 inches. And then this would be 74, and then this would be 76. They just go up by 2. But generically, we would say it like this. This tick mark is mu plus 2 sigmas, and then this tick mark is mu plus 3 sigmas. And we'll almost never have to go higher than 3 sigmas because that pretty much captures everyone in our population for the most part. Now, if I go to the left of the mean, so if this is the average height, then these are taller people. To the left of the mean would be shorter people. So I take mu minus 1 sigma. And then my next tick mark is mu minus 2 sigmas. And then it would be, the third tick mark would be mu minus 3 sigmas. In fact, let's solidify this. So let's say mu is equal to 70 and sigma is equal to 2. Then if I were to change these to numbers, this would be 70, 72, 74, 76. This would be 68, 66, 64. So it really does just represent numbers on a number line, but we're going to learn there's lots of important facts about, what does it mean to be 1 sigma above the mean, or between 1 and minus 1 and plus 1 sigmas between the mean. Okay, then for a sample, it's the exact same curve, but the symbols just change a little bit. So for a sample, the center is not mu anymore, we call it x bar. And then 1 tick mark to the right would be x bar plus 1s. So we just changed the symbol, but the meaning is the same. X bar plus 2 s's, x bar plus 3 s's, and then to the left would be minus those s's, so x bar minus 1s, x bar minus 2 s's, x bar minus 3 s's. So these s's and these sigmas tell us how wide this thing is going to be. In fact, if s is small, if s or sigma are small, that means there's very little variation in this curve, and the curve will tend to be a tall, skinny curve. Okay. On the other hand, if S or sigma are big, you get a very spread out curve. So you get kind of a shorter, wider curve. So this one's saying, okay, everybody's around this average height of whatever. And this one says we've got really tall people, really short people, and a huge spread in between. That's what that says. Okay. Okay, now the last thing I think I need on the theory is an idea of significantly high and significantly low. So if you are above 2 standard deviations, so this would be mu plus 2 sigma, if you're in this region or bigger or higher, this is called significantly high. And it's also for this curve over here. So in the sample curve, if you're 2 S's or more past the mean, that's also significantly high. If you're 2 standard deviations or 2 sigmas below the mean over here, that's called significantly low. And it's the same for over here. 2 S's or smaller would also be significantly low. And we'll learn later on that that basically means you're in the upper 2.5% of people or you're in the lower 2.5% of people. But for now, we just need to know that 2 sigmas, 2 S's, those are the cutoffs for the tails for extremely high values or extremely low values. Okay, so now with that information, we can do the first problem. And I hope I have enough room because I kind of used all my white space here. So the first problem says, the brain volumes in cubic centimeter of 20 brains, n is 20, a little small, but we'll go with that sample size, I guess, just for practice, have a mean of 11.4 cubic centimeters and a standard deviation of 125.3 cubic centimeters. Use the given standard deviation and range rule of thumb to identify the limits separating values for significantly low, significantly high. So first off, we have to match the right symbols to the numbers. So we have a sample because we're only dealing with 20 brains, so we're not looking at all brains of all people. So this is a sample. So when they say things like mean, we look at our little table until we get this figured, until we become comfortable with it. For a sample, a mean, we use the symbol X bar. So this 11.4 is X bar. It says it has a standard deviation of 125.3. So we go to our little table. Standard deviation for a sample is the letter S. So S is 125.3. Now the range rule of thumb, they mention it right here. The range rule of thumb is this. Your significantly low values, to calculate those, you take X bar and you subtract 2 S's. For significantly high, you take X bar and you add 2 S's. Just like I showed down here. It's X bar plus 2 S's, X bar minus 2 S's. So we know the numbers for these though. So it said X bar was 11.4 minus 2 times this 125.3. Is everyone comfortable with how I changed these letters to these numbers based on this problem? Okay, and if you carry out this arithmetic, so double 125, subtract it from 11.4, you will get 860.8. For the significantly high values, you take the same numbers. The only difference is you change this symbol to, you change subtraction to addition. So it becomes plus 2, 125.3. And if you double that number and add it to this number, you will get 1362. And those are the answers for this. Do not round, so I think it turns out to be 860.8 exactly, and then 1362 exactly. Now it says, is the value 1372 significantly high? Well, these two numbers basically say this. It separates this normal curve of brain sizes into these regions, 860.8 and 1362. Any number bigger than 1362 is considered high. Any number smaller than 860.8 is considered low. So is 1372 high? Yes, because it's bigger than 1362. So this 1372 would have showed up over here somewhere. It's in the high region. So is it significantly high? Yes. So all those no's go away. Because it's between the limits separating the values, between the limits would be somewhere in this hump region between these numbers. It's not there. Yes, because it's below the lower limit. Below the lower limit would be somewhere over here in the low tail. It's not there. So yeah, it has to be E. It's above the upper limit, which we, if you plot it, is absolutely true. A lot here. It's getting a little busy with the notes. Is this okay? Okay. Okay, 12. Okay, so 12 is actually pretty simple. It's just identify the symbols we just learned. So the symbol for sample standard deviation. So samples always use our regular alphabet letters. So S's, X's, things like that. Population is where you use the Greek letters. So that's one way to also kind of keep track of them. So sample standard deviation is just S. And you can reference the chart I just built, or if we do enough of these, it'll catch on. The symbol for population standard deviation was that Greek letter sigma. The symbol for sample variance that's S squared. And then for population variance, it's sigma squared. So notice the difference between these two is just you square the number. Okay, so just a symbol review so we can keep that straight. Now in 13, they give us a list of numbers and they say, listed below are prices in dollars for one night at different hotels in a certain region. Find the range, variance, standard deviation of the given sample. Include appropriate units in the results. How useful are the measures of variation for someone searching for them? So in section 3.1, we did things like calculate mean and median and mode, right? And it was pretty simple. Mean was add the numbers, divide by how many numbers. Median was put the numbers in order, find the middle number. Mode was how many times is a certain number repeated, and then that's a mode if it's repeated the most. This is trickier. So this is calculate standard deviation and variance. So let me give you the equations for those. So we're going to give you standard deviation, and then variance is just whatever number you get, square it. So standard deviation S is calculated like this. You're taking a square root of the number of items you have n times the summation of each x value squared minus the summation of all your x values and then squaring it. And then you divide by the number of things you have times the number of things you have minus 1. I didn't used to make, but I used to have students do this by hand in class, at least, just for practice. But even that I've decided is really not useful. Why is it not useful? Because each of these numbers is an x value, okay? Then you have to create a whole new row where you square each of these numbers. So I think we have 8 numbers here, so n is 8 in this problem. So you have to square 8 numbers, then you have to add up all those 8 squared numbers, then you have to add up all the original numbers and then square that, then you have to subtract those 2, then you have to divide by 8 times 7. But even in a problem, I would consider this a small problem, only 8 numbers, this is still a lot of work. So I've given you the equation, there it is. Variance is equal to s squared. So whatever number you get here, you just square it, and that's your variance. I'm going to show you how to do this on the computer so you don't have to do this by hand. And then the last thing is range. Range is actually really easy. You can do this one by hand. Range is just your maximum value minus your minimum value. So that one is easy to do. But let me give you the steps to have the computer do it for you. And that'll save us a lot of work. It's actually the same steps as yesterday, but I'll give them to you again in case you missed that. So next to these numbers in your homework will be this little symbol here. It looks like a window in a window. You're going to click on that, and then you're going to get a drop down that says Open in Statcrunch. So we're going to let Statcrunch do this for us. Then within Statcrunch, there'll be a button called Stat, or a label called Stat. Click that, and then you'll have a drop down. Select Summary Stats from that. And then you'll select Columns, the type of data, because these numbers will appear as a column going up and down in your Statcrunch page. You'll click the words variable 1, and then you'll click compute. And that will take these 8 numbers and it will perform all the statistics we need on them. It will do this equation as one of the things it does. And it will produce a table that looks like this. So these steps will produce the following table. It'll say column, and then it'll say variable 1 because that's what you selected. It will have n, the sample size. In this case, it'll say 8. It will tell you the mean. So it will add up all the numbers and divide by 8. And for this problem, it turns out to be 234.5 for my specific numbers on this page. Then it will say the word variance, which is s squared, and it will spit out 2022.5. Then it will say STD period DEV. What do you think that stands for? Standard deviation. Good. And it will spit out 44.9722. Then it has a column called standard error, which we will use, but not for a while yet. So we can ignore this column, but I'm just going to show it to you so you know. how the table looks when you're trying to do your homework. So this one we're going to ignore for now. Median, so this would have helped for your homework in the previous section because the problems asked for that. In this problem, the median is 238. Then it's going to spit out range, which we need for this problem. And it's going to say 143. And then it's going to give us a minimum and a maximum. The min is 139. The max is 282. So notice this number, 143, is just these two subtracted. And then it gives us a Q1, which we'll learn about in the later on. We'll need that later on, not now. And then it'll give us Q3, which we'll also need later on. So that's what the table looks like. So those steps I gave you, these steps right here, with my numbers will produce this table. And I'm hoping, the whole goal of this is I'm hoping to show you that it's pretty easy to read. Would you agree? So when it asks for problem 1, what is the range of the data? I just go down to the range box and say, oh, the answer is 143. Now, part of this, though, is figuring out the units. So these are dollar values of hotels. So this hotel costs $277, this one costs $258, etc. Range is taking $1 value and subtracting another dollar value so the units are still dollars. It doesn't change the unit. Addition, subtraction do not change units. The standard deviation, so I go down to the standard deviation table. It says 44.97. They want it rounded to 1 decimal. So this 7 would make that a 10, which would trickle up and make that a 45. So this is 45. You'd need the 0.0 to account for the 1 decimal. Standard deviation is also in dollars. Last thing it asks for is variance. Variance from the table, 2022.5. To 1 decimal place, we'll take the whole number, 2022.5. This is where it gets tricky. Variance is your standard deviation squared. So if variance is $45, if standard deviation is $45, variance is $45 squared. So you actually square the number to get to this number, and you square the dollars units to get dollars squared. And this is exactly why we don't use variance. It's very rare to use variance in a statistical analysis because the units get kind of weird. So we know what dollars are, but we don't really have an understanding, well, what does dollars squared mean, right? That unit doesn't make sense. So variance has tricky units and we tend to avoid it. We tend to use standard deviation instead because it's easier to interpret. Okay, so now the last thing is, how useful are the measures of variation for someone searching for a room? So I'm going to kind of help you get this one by reasoning it out this way. When you search for a hotel, do you look for the average hotel cost, or, I mean, average hotel cost might be better than what this is saying. This is saying that the variance of hotel rooms is $45, which means this. Hotel rooms cost X plus or minus 45, plus or minus 90, right? Plus or minus 135. Multiple hotel rooms cost a number X plus or minus multiples of this number. Well, do you care what the range of hotel costs is, or do you just want the best price, right? You probably just want the lowest price for the area you want. So variation numbers are not good for individual choices. What they're used for is for statistical analysis to make business decisions. So if I want to start a hotel chain and I know that I can get away with charging, where's my mean at? I can get away with charging $234 plus or minus 45, then I can get a range of how much money I'm going to make. So for someone searching for a room, the measures of variation are not very useful. And again, because they say, what are you going to, the individual person cares about low price, good location, accommodations, things like that. So these sorts of statistics don't really come into play until we start making, business decisions, things that I'm going to be dealing with hundreds of customers, and I need to get a sense of what all those people are going to do. Questions on that one? So it's mostly just getting these steps in the computer correctly and interpreting the table. And if it were a paper test, I'm not sure how we're going to do tests in this class for this semester, but if it was a paper test and I'd asked a problem like this, I would always give you the table. So you would see this printout, and then it's just, grabbing the right thing. Because we're mostly interested in this course anyway in how you interpret the numbers, not getting the numbers. Okay, 14. It's the same steps as before, so I'm not going to go through those again. We have, this is the amounts in dollars it costs for marriage proposal packages at different baseball stadiums. Who's proposing at a baseball stadium? I don't know. It seems like a stupid idea. Find the range, variance, and standard deviation for the sample. Include appropriate units. So same steps as 13. That was a joke. So if any of you have been proposed to at a baseball stadium, I say more power to you. Not something I would do. Okay, the range of the sample data. So you do those same steps, and then this will spit out $2463. That's the range. Standard deviation on this one would be $755. Oops, $755. And then again, the variance, this is where it gets tricky. It's going to be a big number because this is pretty big. $800 squared is going to be pretty large. And in fact, in this one, it's 570063.6. And then here's the weird thing. The units are dollars squared again. But this problem asks an interesting one. So let's just look at this data. And they organize it from smallest to biggest for us to make it easier. Any things you see here that are a little bit alarming? Yeah, so I kind of see something going on here, right? So we're in the hundreds, right? So back here we're even in the tens, but it increments kind of reasonably. And then this is literally almost 4 times bigger than that. So this is an example where there's a good chance that the person typing this in probably accidentally added a 0. They probably fat fingered it and hit a 0 twice there. So these numbers probably should have been 200 and 250. And you kind of can see it here, like this range is really high because this number is really big and this number is comparatively small. And then your standard deviation gets huge. And because of that, your variance is enormous, 570,000. So this is kind of a dead giveaway that we've got a problem here. These are called outliers. We studied that term a chapter or so ago. So are there any outliers? Yes. So this no one is out. The answer is C. Let's just make sure it sounds right. The largest amounts are much higher than the rest of the data and appear to be outliers. It is likely that these are having a large effect on the measures of variation. And that's true. So they're going to jack up your numbers really by quite a bit. Okay. Now we're going to learn in this class, you don't necessarily just get rid of outliers. You should study that. So as a statistician or a business person in the future, if you're given a report like this, you should say, ooh, what's unique about these two stadiums that requires them to charge so much? And then you either find out that it's a typo, or you find out that, you know, maybe they have some kind of luxurious location or something that warrants such a high price. Okay, 15. The only difference in 15, it's going to be the same steps as before, but when you get to where you have to select variable, so there's a step in those directions I gave you where it says click variable 1. You're also going to have to, for this problem, hold down the control key, and then you're going to click variable 2. So basically you want to capture both variable 1 and variable 2, and then your table will end up having 3 rows: a title, a heading row, a variable 1 row, and then a variable 2 row. And you can get the same information for both sets of data. Okay. This one is amounts in millions of dollars collected from parking meters by a security service company and other companies during similar time periods. Do the limited data listed here show evidence of stealing by the security service company's employees? So very interesting. They want to look at the variation in these numbers to see if maybe there's evidence that someone's pilfering the quarters from the meters. Okay, so they asked for the coefficients of variation. Coefficients of variation, which we're going to call CV. To get them, we do have to do this by hand. So the coefficient of variation is equal to the standard deviation S divided by the mean X bar. And then you multiply by 100% to turn it into a kind of a probability number. Okay, so the whole reason you need to do these summary stats on this problem is to get a standard deviation for the first company, and then a mean for the first company, and then a standard deviation for the second company, and a mean. So you need these 4 numbers. And if you do this, you will get the following. So the CV, the coefficient of variation for for security service company would be, actually let me just call this for variable 1, would be S over X. The S for that one is 0.125, and the X bar is 1.53. And when you divide those two numbers and multiply by 100%, you will get 8.2%. The coefficient of variation for variable 2 is, again, S over X bar, standard deviation over mean. And for this one, it's 0.137 divided by 1.71 times 100%. And if you do that math, you will get 8.0%. So now we just look at these two numbers and say, okay, coefficient of variation. So the higher this number, the more varied the numbers are. So the lower this is, the more the numbers are close to each other. They're pretty much the same number. So these are pretty low. But what we actually want to look at is how close are these two numbers to each other? And I would argue they're only 0.2% off, right? So do the limited data show evidence of stealing? Basically, this company's variation is almost the same as all other security companies. So that would be no, there's not evidence of stealing. There is not a significant difference in the variation, C. Perfect question, because we're going to answer that in the next question. So what would be a big difference? So let's look at 16. This is the waiting line, the waiting times at banks. In fact, we saw this problem. We just analyzed it last class. Single line, so we all get in one big line, versus like the grocery store, individual checkouts where we can get in the line that we think is going to be the fastest. So you're going to do the same steps as 15. You need Statcrunch to get S's and X bars, divide them, multiply by 100%. But what you will find is this. For the first bank, the coefficient of variation is 6.7%. And for the second bank, it's 25.5%. And remember, we had kind of talked about this. I used the example of I'm on a lunch break. I only have 8 minutes and I need to go to one of these. And I said, well, I'm going to avoid bank B. Why did I say that? Because it could take anywhere from 4 minutes to 10 minutes. And I can't afford that kind of variability. I need bank A because it's only going to be between 6 and 8 minutes maximum, right? So even though I might get through bank B faster, there's a risk there because it could very well take 10 minutes. And here's how it shows up mathematically. The coefficient of variation is a huge difference, I would argue, right? This one is 3 times, this is 3 times bigger than that. And we can see it in the numbers. So these numbers in bank B are much more varied, so you get a higher variation number. These numbers are all pretty much close to the same, 6 and 7, so you get a low variation number. And again, it's about planning. So I can predict this number with little probability of mistake. This could be a huge difference in what I expect from what I get. So is there a difference in variation? Yes. And it turns out the waiting times at bank A have considerably less variation than those at B. Does that problem help you see the usefulness of this sort of statistic? Because it's for planning, right? So the higher this number, the harder it is to plan because things are kind of all over the place. Okay, 17. It looks complicated, but it's actually one of the easier ones on here. It says, use the body temperatures in degrees Fahrenheit listed in the accompanying table. The range of the data is 3.2 degrees. So let's write that. Range equals 3.2. Use the range rule of thumb to estimate the value of the standard deviation. Compare the results to the actual standard deviation of 0.70. So the range rule of thumb says this. You can estimate your standard deviation S by taking the range value you have and dividing by 4. So it's a very simple calculation. Just divide your range by 4 instead of, right? So the other way to do it would be that formula I gave you where you have to square each of these numbers, add them all up. With this many numbers, to do this by hand would be extremely difficult. Or you could let the computer spit it out for you, but this is even easier. Just find your biggest number, find your smallest number, subtract them, get this number here, divide by 4. So in this one, you would just take S is equal to 3.2, the range, divided by 4, and you would get 0.80. And that's a very rough estimate. But then they say, oh, compare that to the actual. So they did all these 50 numbers or how many there are. They ran it through the computer and got the actual standard deviation to be 0.70. And basically we can say that these are pretty close. So 0.70 and 0.80 are only 0.10 degrees Fahrenheit off. So the estimated standard deviation is within 0.2 degrees of the actual. So this was within 0.20 degrees Fahrenheit of the actual standard deviation. Thus, the estimated standard deviation meets the goal. So we can shortcut our math by a lot with that very simple shortcut. Okay, I want to do 18 last because it's the hardest one on here. And if we run out of time, then we'll have to finish it next time. So let's do the easy ones, the vocab word ones. So 19, which of the following is not a property of the standard deviation? The standard deviation is a measure of variation of all data values from the mean. That's exactly what it is. The value of the standard deviation is never negative. So if we go back to the equation, you're taking your x values and squaring them. That guarantees you get positive number, right? Because if you square negatives, you get positives. You add up all your numbers and you square them. That guarantees you're going to get a positive value. This number will always be bigger than this number. So subtracting this number from this number will always be positive. N will always be positive. So you can never get a negative value out of this. So that's true. When comparing variation in samples with very different means, it is good practice to compare the two sample standard deviation. Come back to that. The units of the standard deviation are the same as the units of the original data. That's true. So in the hotel rooms, when the original data was dollars, the standard deviation was dollars. So the units will always match. So C is the only one that doesn't fit. So comparing variation and comparing standard deviations, it's the same number. One squared, the other's not. So if they have very different means, using one over the other doesn't do you any good. It doesn't change it at all. Okay, last one, and then we'll go back. I think we'll have time to do 18 still. For data sets having a distribution that is approximately bell-shaped, blank states that about 68% of all data fall within one standard deviation from the mean. This is called the empirical rule. I'm just going to give it to you. The empirical rule says this. I'm only going to briefly touch on it because we're going to study it in detail in many sections. It says this: between the first -1 and +1 standard deviations, 68% of people are between that. It says between the second standard deviation, if it says between -2 and +2, 95% of people are between those two. And then it says something about the third one, but we'll save that. So it's a good way to estimate how many people are going to fit in these different heights if we're using height or whatever it is. Okay, so let's go back to 18 and see if we can do this in the last 5 minutes here. So the tricky part about this one is it's a frequency distribution, and there's no way that I know of to make Statcrunch do this for you, so you can't do this one with the computer. So the first thing you have to do in a problem like this is create a new row. Called X. And X, which you see in the equation here, is the midpoint. So we have seen that before. It's the middle number between these two numbers. And in this case, it'd be 24.5, 34.5, 44.5. You see the pattern here. Going up by 10, 74.5, 84.5. Okay, so everywhere you see an X, you're going to use these numbers here. So what this formula says is square each of these X values. So if I were doing this problem, I would create another row called X squared. And I would square each of these numbers that I just wrote down. And I can give you a couple just so you can try to match this up later. If you square the first one, 24.5, you'll get 600.25. Then the second one gives you 1190.25. Dot, 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 etc. Fill in the rest. Okay, so each of these numbers down here is F, frequency. So this says, take your x squared value, this 600, times its F value. So you'll take 600 times 2, and then you'll add those up. So you'll take 600 times 2, 1190 times 4, this number times 9, this number times 2, and then you're going to add all those up, all those answers. This part says subtract from that number each F times X. So you'll take each F times this number. So 24.5 times 2, 34.5 times 4, 44.5 times 9. And you're going to add up all those. Add up all those and then square that number. And then you'll divide by n. To get n, you're going to add up all these frequencies. We've actually done that before. Add up all these numbers, and that gives you n. It is a bit of work, but try it. It can be done. If you do that, if you do all these steps for this problem, you will get a standard deviation of 15.5. Then it says consider a difference of 20% between two values significant. How does this compare with the given standard deviation of 11.1? So they basically did this math with all the original numbers, got a standard deviation of 11.1, and it turns out that our estimate is significantly greater than that one. All right, so that will do it for 3.2.